Uh, Once again, good afternoon. Uh, Today we'll move forward to where we stopped last time. That is, last time we did first order first order system time response. Today we'll continue with second order time response system. And before we start second order time response system, I remember that last week I skipped system representation. Actually, this is same as the standard forms we saw last time, but today we just tackle it in general form. So after that, we won't do first order example as it is shown there, because I think most of you guys did the practice question, and no one actually show if he or she has a problem, except one or two. So I assume all of you guys were okay with that practice problem for first order system. And then we'll move to second order system time response and design specification for second order time response system. So for system representation, we have two forms. We have pole zero form, and also we have a constant time constant form. So for a pole zero form, you can see from this equation g of s, and we have numerator and the denominator. In the numerator we have a constant, and all the numerator, the whole of numerator is being factored, also the whole of denominator. So you can see we have into bracket s plus z1 into s plus z2 till s plus zm. So let's say our our last pole is actually z, or zero is actually zm, and same thing with the denominator. So when you arrange your system or a transfer function into this form, then we say this is a pole zero form. And from here, we can actually factor s in the denominator such that we have s to the power of r, and then uh, into bracket s plus p, s plus p2, s plus p3. So the good thing with this is that we can actually define a system or have a system with this integral or with this denominator s to the power of 3. So if you have a system such that you have factored into this form, pole zero form, and then you have a s and r is just 0, then we call that system a type 0 system. And if we have 1, then we say this will just be s to the power of 1, so it's just s. Then we'll say that is a type 1 system, until we have like r is equals to 2, then we say that is a type 2 system. And this notation of poles and zero, let's say we have an s-plane. So this is the imaginary part and this is the real part. So when we say a pole, as we're seeing here, zeros and poles, then what we mean with pole, we denote pole by an x. So we can say maybe that is a p1, and this is maybe is a p2 from here. And for zero, we just denote with a circle. So for poles, you equate denominator to 0, and then you find those roots. The roots of the denominator is actually the poles of the system, and the root of the numerator is the zeros of the system. Because if you put P1 here, the value of P1, this thing will actually blow up. Will have a pole as infinity. That's why we call it a pole. Because if this is, let's say this is minus s, then the whole system will go to infinity. So that's why we say these are actually poles, and the zeros, when we have a zero here, this will go, the whole system will go to zero. Then we say those are zeros. So the way we show them is by x pole and zero by and zero with a circle. So this R here is the one which decide which type of a system is. So if R is zero, then it means we don't have this S here, and this S is actually a pole at the origin. So if this is just one, then it means we have a one pole at the origin. If it's two, it means we have two poles at the origin. So that is a pole zero form of the system, and we'll use this in designing and analysis later. For a time constant system or form, we can actually rearrange our transfer function so that we have in this form. And once you have that in this form, then it means the poles and zeros are actually the time constants, the time constant of the system, as you can see here. So when I say pole, I mean S tau plus 1, and then I put this to 0. So I'll have tau pi or tau p1 equals to minus 1. Sorry, S is actually equals to minus 1 over tau p1 for this case here. So we equate this to 0 to get the pole of that system. So you can see actually the pole, once you arrange in this form, then it means the poles are actually reciprocal of the time constant. So those are the two forms, or the way we can represent the system. So we can present either in pole zero system and in pole zero form, or in time constant form. Now we go back to our second order system. So for many of the physical system are actually second order, and those which are higher order, they can be approximated to second order system. So it's very important that we discuss second order system. So there is no need to, once you have modeled a system and the system is maybe to the power of 4 or to the power of 3, it's easier to remodel that system to a second order, because many of the tools are standardized in second order system. So for a second order system, which is a type 1 system, a type 1, it means you can see here we have S to the power of 1. So this is a type 1 system. And the overall transfer function is given by that. So you know this, you have K. If this is G, then it's just G1 plus G, because our H here is 1. So once you plug in this in as G and that as G, you rearrange, you will end up with with this equation as your overall transfer function. And if we put it in standard form, then we divide by tau, divide by tau up and down. So we end up with this equation k over tau s over s squared plus s over tau plus k over tau. And this can also be modeled, rearranged into this form. So this is actually the form which we'll use as a second order system, where this is actually k over tau square root, and delta is the damping factor. So this is natural frequency squared, and this is also natural frequency squared. So any second order system you can actually compare with this general one, such that we have a numerator as omega n squared and denominator a quadratic equation, which is characterized by delta and natural frequency. The denominator, this denominator, as we are seeing it here, we call this denominator a polynomial, characteristic polynomial. So this is actually a characteristic polynomial. And when we set this denominator to 0, we call this a characteristic equation. So this is a characteristic equation of a second order system, which has two variables. It is being characterized by delta, damping ratio, and natural frequency. As I said, it is characterized by damping ratio delta and natural frequency omega n. And this natural frequency is in radians per second. Some problems I give, I just say natural frequency is like 2 hertz. Then you need to convert that to omega n. What we can do now is actually analyze this system in terms of step input. And the way we do it is we analyze in using different delta or different damping ratio. So we'll see for when delta is 0, how the system will behave with a step input, and when delta is greater than 0 but less than 1, so actually a positive but less than 1, and case 3 when delta is 1, and case 4 when delta is actually greater than 1. So for input step input, this value 1 over s, and this is our this is rs, and this is transfer function. So the output in terms of Laplace is given by this, where this is the input. This is our rs, our rs. So when delta is equals to 0, when delta is equals to 0, it means we'll have s squared, so this will go off. When d is equals to 0, we'll have s squared plus omega n squared multiplied by this. So this will go to 0. So we'll have something like this. When we separate and do and perform inverse Laplace transform, we'll have our response as this. So from here we can actually see that this response has a constant of omega n, and this cos omega n, it means there will be some oscillation. So for case 1, we call it undamped system, And this undamped system has sustained oscillation. We have oscillations that will never stop. So this is not good for our systems, because we don't want the system to vary every now and then. We want a system to attain the desired value. So because we can see here, this is our input one, and this is output. So the output is actually oscillating around the input, and this, remember, this is also the one we desire, one. So this system cannot work. So whenever you have delta is equals to 0, just know that we'll have oscillation with a constant frequency of omega n, and these oscillations are actually sustained, and the system is called undamped system. Why? Because the poles of these are imaginary. The poles of these are imaginary. So we have one here and another one here. So maybe this is j omega n, and this is minus j omega n. Another case is when delta is greater than 0 but less than 1. When you do partial fraction and a lot of manipulation and mathematics, algebra, you will end and taking inverse Laplace transform, you will end up with S of t response given by that, and that is given by that. So by the way, in exam, I won't tell you to derive this. This is too long. Us will just analyze the equation. So for delta greater than 0 but less than 1, you'll end up with a time response given by that, which can be reduced to this, where the omega d is actually damped natural frequency, and this is a natural frequency. And this theta is given by that. Tan theta is given by that equation. So let's analyze this as t goes to infinity. You see this t, as this t increases, then it means these oscillations will be decreasing, because this part is the one which is responsible for this up and down here, the sine and cosine. But these sine and cosine, these oscillations are actually decreasing because of this factor. We have minus delta. So minus delta omega n t. So when this t increases, this part is actually reducing. As this goes very, very big, t goes big, it means this factor goes to a very small number, such that you can say it goes to 0 as t goes to infinity. Then we'll have ct is actually 1 minus 0. Ct is equals to 1, as you can see here. We observe that the response ct is that oscillation. We have oscillation, but they are damped, they are increasing, which tends to 1 as t tends to infinity because of this factor here. So we say this system is undamped system. So, and the value which in control is being used is actually 0.4 to 0.7. Most of the time, delta 0.7, we have only one oscillation, and then it goes to the desired value, which is 1. So most of the time we use delta is equals to 0.7. When you are given a problem and delta is not mentioned, which is rare, then you can use delta is equals to 0.7, or you are told to use appropriate uh, uh, delta value or damping ratio value for your system to be stable. You can use delta 0.7. So we say this system is undamped system. Another case is when delta is equals to 1. So when delta is equals to 1, we have two real double pole. So we have their real values, they're just here. And as this S of C of t goes to 1, as t goes to infinity, we say this value is a critically damped system. You can see between this system and the previous one, this actually takes longer to reach here, but the previous one goes here with oscillation and then stabilizes. This is for 0.7. So for 0.7, we'll have a system like that. And for 1, you have a system which a little bit sluggish. It's slow. So we call this system critically damped system. So whenever you are told the system is critically damped, so just know delta is equals to 1. Another case is when delta is greater than 1. So when delta is greater than 1, it is actually the same as this critically damped, but it takes much longer to reach this part. You can see the critical damp was like here, and this is an overdamp. So as we go, we are increasing delta, we go to this side. As we are decreasing, we go to that side. So this takes a lot of time than the critical damp system. And we call this system an overdamped system. So this is example of a system, time response system with step input for second order. You can see here we have delta is equals to 0 here. With delta is equals to 0, you see we have oscillations which are sustained. They'll go on forever like that, and we don't want that. And then when we have a value of 0.1, you can see this is 0.1, 0.2, 0.3. So 0.1, we have this with some oscillations, 0.3, 0.4, but around 0.7 here, we just have like one oscillation, and then it goes to the desired value or the input. So the way is we look at between 0 and this value, and then we say, okay, 0.7 is the value which can give optimum response. So we'll go with 0.7 because, okay, we have an oscillation, but only one, and then it stabilizes. So we can say we can sacrifice with one oscillation, but we have a faster response rather than going to 1, 1.5, and 2, which they take time. You see this, but 0.7, so we can go with 0.7. Actually, you can simulate this in MATLAB so that you can actually see for yourself. So the way we design is that we use some specification for second order. So performance of a system is actually evaluated in terms of this quality, which we have been talking about, the way to how fast it will reach input, how fast it will reach the desired output, the error between output and input. Remember, we talked about steady state error and oscillations around the desired value. So oscillations around desired values are actually this one. So this is our desired value, which is also the input. So you can see we have oscillations there. So we don't want this oscillation. We can have like one, so that we have a faster response rather than having a 2 delta 2, which takes time to reach the desired value. So the way we do this is actually define some parameters where we use for we'll use for our design. We have time delay, rise time, peak time, settling time, and we have maximum overshoot value. So delay time TD, this one, this is time required for response to reach 50% of the steady state value for the first time. So time which value reaches 50% of the steady state value is actually a time delay delay specification. And rise time, this is the time required for response to reach 100% of the steady state value for underdamped system. But for overdamped system, then you take the rise time between 10% to 90% of the steady state value, and the equations and the equation for underdamped system are actually these ones. So TR is pi minus phi into this, into damped frequency. So you can have it as this. Over phi divided by omega d, divided by omega d. So this is the rise time. For peak time, it is the time required for the response to reach the maximum peak, which is MP. So this is the highest peak, first highest peak. So at this time, this time is actually the peak time. So this is first peak. This is first peak. Second peak is this, and that is third, and this is fourth, and this is first undershoot peak. This is first undershoot peak, second undershoot peak, and this third undershoot peak. So from this equation, we have Tp is equals to phi of omega d. So this is actually the first here, Tp. So if you want to get the time for the second peak is actually what you do, you multiply by 3. So here you say first peak is this, second peak it will be times 3. Why? Because this is the first time they peak, and then this is second, and this is third. But this one is actually undershoot. So when you are told to get second peak of the system, you multiply by 3. And when you are told to get first undershoot, you multiply by 2. So this will be by 3, 1, 1, 2, 3, 4. So the third one will be 5. And peak overshoot is defined as the difference between the peak of the response and the steady state. This value here, between here, this is the steady state. So this value here minus this value. So this is MP. Peak overshoot MP. It is defined as the difference between the peak value of the response and the steady state value. And normally this is expressed in percentage. So you will be told like MP is 20%. And you can calculate MP in terms of using this equation, which variable is only the damping ratio. All these equations are in the notes. So, and remember this is actually an exponent. For settling time, it is actually the time required for the response to reach and remain within a specified limit. And this limit we normally use plus or minus 2% or plus or minus 5%. So this is the tolerance band. So we can have between here and here. Maybe this is plus 2% and this is minus 2%. So we can have you'll be told like the tolerance is 5% plus or minus 5% or is 2 plus or minus 2%. So it is given by this. So for 2%, you have 0.002, and when we assume that this is very, very small, delta is small, then it means this value will just be 1. So once we have that, we can just have this numerator is equals to 0.02, taking ln on both sides, we arrive with our settling time is equals to 4 over delta omega n. Remember, this formula is for 2% tolerance. For 3%, for 5%, sorry, if you do same thing like this, you'll have 3 here. As so for 5%, you can use this. You set this to 1, and then you'll have your settling time as 3 over delta omega n. Another design parameter or specification is the steady state error. We saw this. So steady state error is actually error between the desired output and actual output as t goes to infinity, and it is given by this. We also show that you can actually use final value theorem to calculate steady state error. And for this system, type 1 system with unit step input, our steady state error is actually equals to 0. So that is actually what I wanted to discuss today. Unless there is any question or any example that you didn't follow or you need clarification, you can ask. Tomorrow we'll start with steady state error analysis. So any question? Class.
A question has been asked in the chat.
Asema, what is the steady state error for undamped system? Let me just share with. So he's saying what is the steady state error for the undamped system? Actually, you can do this as your as assignment, or we can try here. So we know error is actually RT minus what? Minus CT. Input minus output. So we have our input as 1 minus 1, and then this will be plus minus 1, and then that will be plus cos, like that. So we end up with ET is equals to a cos term with N is equals to that. So ESS is when lim goes to infinity as t goes to infinity. So cos of infinity is what? Class. Class. Cos of infinity.
Undefined.
Undefined. So why? Because when you say when it's undefined, then it means that we cannot actually get a value, because this is these oscillations are actually sustained. Sustained means they'll go on forever. They'll go on forever. So they won't decline until we switch off a system. That's why this is because of. So we cannot actually get a steady state error, and this system we cannot use this system because actually this is just oscillating around the desired value or the steady state value, not the steady state, the input value. It's just oscillating around the input value, and it will go on forever. So we can, if it's undefined, cos of omega, cos of infinity, then it means that this the steady state error, we cannot get a value of a steady state error for that system. Anyone else? A question from last week class, someone is asking a question. The last week class discussed the TF was already given in the statement. Why did we still do transfer function G1 over, yeah, Okay, let me see the question. Can you read the question? Who is this? Chirono.
It was the example exercise one.
Example exercise.
There's one in the notes. It was the open loop plant transfer function of a unique feedback linear time invariant control system is given as G equal 1 over S plus 2. Use Laplace transform to derive an expression for the time response and sketch the response. So they say the transfer function is given as G equal 1 over S plus 2. But we went ahead to use the G and the H as 1 to get the transfer function. So I was wondering the transfer function, the one given the
Let me just check. Let me check the question. Where is it? Yeah. Just a minute, I'm looking at it. Okay. So let me just share and we look together this problem. Okay. Can you see my screen?
Yes.
So this is the question, exercise 3.1. The open loop transfer function, the open loop plant transfer function of a unity feedback. So is that the question?
Yes, it is.
So you see, he's saying the open loop transfer function. So the open loop, this is G. And also he said that of a unity feedback system. Of a unity feedback system. So it means this GP is actually the G on the forward path of the transfer of the system, and then we have a unity feedback to it. That's why we went and let me see if I can actually. No. So what he's saying is actually, you see this block, this is the forward path of the open loop system, the open loop transfer function. This is the GP, and then it has a unity feedback. That's why we went on and did G over 1 plus G. You understand,
Yes.
madam?
Yes, yes.
So
yes.
this is the open loop is this G without feedback, and then he's saying it is a unity feedback system. You understand now? So you need to apply that 1 over G plus 2. I know why you are saying that maybe you saw some solution from previous past papers. Uh, I also saw that it was wrong the way it was done. I know some there is a previous exam question with solution letter someone did with only 1/s+2, but remember he's saying in the question we have a unity feedback, and this is an open loop. So this is the open loop transfer function. And then you need to apply G over 1 plus G to get the full transfer function. So that is the way I know it's supposed to be. Sawa sawa.
Yes, yes, thank you.
And another thing, you need to you guys those practice questions are very important. When I say you do and practice, please do practice. If you want, you can you can submit and look at it and correct it, even give you a solution. But a solution, it will be I'll just send you to that particular student solution. So those who did those practice questions, either they did it right, I'll say this is correct, and something which is wrong, I'll correct them and even give them solutions. So if you want, you can just submit and look at it and do some correction if there is a need to. If it is correct, I'll just tell you that is correct. Another person is asking for system representation. Did you mean that when R is equals to 0, when R is equals to 0, there is no pole at the origin? Yeah. When R is equals to 0, it means S is power. S is the S to the power of 0. So S to the power of 0 is 1. So it means we don't have a pole at the origin. So that is a type 0 system. So any system which doesn't have a pole at the origin, we say that is a type 0 system. A system which has one pole at the origin, we say that is a type 1 system. A system which has 2 poles at the origin, we say that is a type 2 system. As simple as that. Any other question? I understand that today we have only 64 guys reading for the supplementary. Any other question? If we don't have any question, then we can meet tomorrow for steady state error analysis. For steady state error analysis. I've also posted some questions, practice questions. You can try to do those questions. Thank you.
Thank you.
lives.